Hello, AP Statistics students. Today in our lesson, we're going to take a bit more thorough look at a sampling distribution of means. To make sure we got that, couple more topics, but we are getting close to the end here, everybody. I'm pretty sure our exam is going to land next week sometime. So FYI, that is coming. We are almost done with sampling distributions. All right, but we just kind of introduced this last week on a Friday. I realized it was a Friday, so we should probably talk about it some more. So sampling distributions of means, we're going to describe them, and we are going to find some probabilities using them once we ensure they are normal. All right. You got another homework assignment up on sampling for you, and we will keep our quizzes rolling with quiz 4 on Wednesday. All right, let's do this. Sampling distribution of means. So first off is we got to make sure that our sampling distribution of means is normal. All right, so when is this sampling distribution normal? All right, it is normal if one of two things is true. All right, if you happen to know that your population is normal, then your sampling distribution will be normal pretty much no matter what. So it's all good and you're done. Okay? If you know the population is normal. Now, to be honest, you almost never know that. If you knew that much about a population, you wouldn't be doing statistics in the first place because you would know the parameters. So usually we don't know that. Usually we have to take the second condition that needs to be true is if the samples you are taking, if n is greater than or equal to 30. If you just take a big enough sample, the sampling distribution will be normal. But with means, there's no n times p, n times q. There's no proportion, right? It's just the sample size has to be bigger than 30 or equal to 30. That will do it. Hopefully you saw that when you filled out the table from Friday. If your sample size is big enough, then you have a normal sampling distribution, and 30 is sort of the agreed upon number. Okay, there's no magic about 30, it's just the agreed upon number. That idea, though, is kind of groundbreaking, that even if your population is skewed, you still get a normal distribution, even if it's bimodal, even if it's completely some random distribution. If I take 30 or more in a sample, the sampling distribution of averages will be normal. And that's such a groundbreaking idea, it is called the central limit theorem. Okay, that is huge. The central limit theorem is that if you take sample sizes that are big enough, a sampling distribution of means will be normal. All right, so that's the shape. That's how you get the shape. What about the center? Well, the center, mu, of all the x bars, all right, the average of all the x bars will be equal to the population average, just straight up mu, because, all right, means are unbiased. So the sampling distribution will be centered on the population parameter. I know the Greek here looks a little weird. Remember, that mu right there is the population parameter. Whatever is true for the whole population. And for spread, the last one, the standard deviation of all the x bars will be equal to the standard deviation of the population divided by the square root of the sample size. Variability will shrink. All right, your normal model will get narrower the bigger your sample is. All right, if you take a larger and larger sample, there's much less variability. The average will get closer to the true average. All right, those are the main points of a sampling distribution. Let's put it into practice with a few problems. All right, so first, been to the movies recently? No, I have not. The number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies with a standard deviation of 15.8. Suppose we take an SRS of 100 students. All right, calculate X bar, the mean number of movies viewed by the members of the sample. All right, so what would this sampling distribution of X bars look like? Remember, sampling distribution. These are all the X bars. So we're imagining taking sample after sample after sample of 100 students. All right. What would that distribution look like? Well, the shape. What would our shape look like? Well, the shape is normal because n is equal to 100, which is, in fact, yes, greater than or equal to 30. Check. All right. Our shape is normal. Our sample size is big enough. And yes, you do have to compare it to 30. Okay, you do need to say something like that. All right, what about our center? All right, well, we know that the average is 19.3 for the entire population. So the average of all my X bars should also be, or at least the center of the sampling distribution, should be, on that value of 19.3. All right, well, we can start building our sampling distribution. 19.3. There, and now, oh, I need the standard deviation, don't I? All right, so the standard deviation, the spread is going to, so the standard deviation of all the X bars is equal to, all right, well, the population was 15.8, but I am taking samples of 100, so I will divide by the square root of 100. I don't have to do that on the calculator, do I? Because that's divided by 10, so that is equal to 1.58. So we know the standard deviation is 1.58. So plus 1.58 minus 1.58 in each direction. Our standard deviation of all the X bars is equal to 1.58. Alrighty. So what are the chances, now that I know what these samples should look like? Remember, I should even gotta say it one more time. Each dot in this distribution, okay, I'm gonna ask you, hey, what does that dot right there represent? I'm gonna do it. All right, that dot right there represents the average number of movies watched by a sample of 100 students. Okay, that's going to be the whatever number that might be, 15 or 16, whatever it happens to be. It's the average of 100 kids. All right, what are the chances of getting a sample where the total number of movies watched is 2,500? All right, this is a popular thing for textbooks and test questions to do, is to not frame the question in terms of an average, but to frame the question in terms of a total. So if the total number of movies in this sample of 100 is 2,500, well, then the average had to be 2,500 over 100, which would be 25. All right, if the average kid watched 25 movies, and I have 100 kids, that means there was a total of 2,500 movies. Not different movies, but 2,500 views total. That's a popular way to phrase these questions. So now we're going to find the probability that X bar is, oh, I got to put more than, not exactly. Oops. Let's, more than or less than. What should we do, everybody? More than or less than is, let's go more. All right, more than. We can't have discrete values here, right? There we go. More than 2,500. All right, greater than 25. Well, not X bar. X bar is only 25. but that will give us 2,500 movies watched. All right, so, well, that's just going to be a normal CDF, right? We got 19.3 as our center. 25 is somewhere out here, I guess. And then shade that in. So let's do our normal CDF. Second distribution, normal CDF. Lower is 25, upper is infinity. The mean is 19.3, and the standard deviation is 1.58. Ooh, this is a good reminder. Remember what that little negative right there means, that little guy? Do not tell me 1.54. It is not 154%. It is not 1.5%. When you get a number that doesn't make sense, look over here at the E. This is E negative 4. All right, so that means this is 0.0000154. All right, we took that decimal place and moved it once, twice, thrice. Thrice? Thrice? I'm going to go with thrice. All right, 4 times over. All right, 0.000154. So there's almost no chance of this happening because that is a 0.01% chance. All right, I know a lot of decimal place moving, but to get the probability, I had to move it over 4. To turn it into a percent, I had to move it back 2. Okay? So, 0.01% chance that we have a total of more than 2,500 movies, or of an average bigger than 25. All right, let's do one more together here. If you want to pause the video and try this one out without me, that'd be a great idea, but I'm going to go ahead and work this one out for you, with you, for you, whatever. Keith. Keith. Keith is the manager of an auto care center. Based on service records from the past year, the time in hours that a technician requires to complete a standard oil change, why'd they say in hours when they're going to give it to me in minutes? Interesting. Follows a right skewed distribution with a mean of 30 minutes and a standard deviation of 20 minutes. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Keith budgets an average of 35 minutes per customer. That's how much he's budgeting. Will that be enough? Okay, so the population, there's an average of 30 with a standard deviation of 20. He's going to take a sample size of 40, essentially, right, and give them the coupon. But he's allotting more than the average, right, because some of them will take more than 30 minutes. He's allotting 35. Will that be enough to cover all of it? Because some of them are going to take less, right, but some of them will take more. All right, calculate the probability that the average time it takes to complete the work exceeds 35 minutes. All right, the average time in my sample of 40. All right, so we're taking samples of 40 people here. So the shape is, in fact, normal. All right, because our sample size is equal to 40, which is greater than or equal to 30. Check. All right, shape, the center. All right, so if I take samples of 40 customers, the average time is going to be centered around 30 minutes, the true average. All right, the standard deviation is going to be equal to, of all the x bars, is going to be equal to 20 over the square root of 40. I don't think I can do that one in my head. All right, 20 divided by the square root of 40. 3.16. All right, so here is what a sample of 40 customers could look like. All right, click, click, click. So Keith is budgeting an average of 35. So what are the chances that a sample of 40 exceeds an average of 45 or 35 minutes? All right, because if the sample exceeds 35 minutes as an average, he didn't budget enough time. All right, the lows didn't balance out his highs, and he went over. Hopefully you see that as simply a normal CDF. Again, second distribution, normal CDF. Lower is 35, upper mean is 30, 3.16 for our standard deviation. So there is a 5% chance, 0.056. So the probability that an average sample will exceed 35 minutes. I don't really need the equal to sign. These are continuous variables. All right, is equal to 0.0, what did I say, 5.6? Yeah, I go 5.7. Yeah, 5.67. There we go. So there's a 5.6% chance he didn't allot enough time. All right, to do all the oil changes. All right, B, how much average time per customer should Keith budget if he wants to be 99% certain he doesn't go over budget? Okay, so right now, Keith has a 5.6% chance of being over budget. That means he is 94.4, I think, percent sure that he's gonna make it. There's a 94.4% chance that he did allot enough time. But what if he wants to be 99% sure? What if he wants to turn this number and make it bigger? He wants that number to be 99%. Well, he's got to shift the 35 over, doesn't he? He has to like 36, 37, 38 minutes. He has to shift it over. Well, where is that boundary going to be so that there's 99% on the left? All right, so here's my normal model. I want 99% over here, which means I'm going to have 1% over here. Where is the boundary? Huh? How are we going to do that? I'm hoping this is coming back to you. How do we go backwards? I gave you an area. I want the boundary. That is an inverse norm. Right? It inverses the operation. It goes backwards. Inverse norm. What's my area? I want 0.99. What's the average? 30. What's the standard deviation? 3.16. And it will tell me where the boundary is for 99% to the left. So 37.35. All right, 37.35. All right, so we inverse norms. Area equals 0.99. And then the average, 30, and the standard deviation was 3.16. And so we got 37.35 minutes. If he wants to be 99% sure he budgets enough time. All right, there we have it, everybody. Again, not new skills, I'm hoping. Normal CDF, we've done that. We've done all that. The new stuff here is just describing the distribution. When is it normal? And what is the new standard deviation for sample sizes of a certain size. All right, everybody. That's all I got for you. You can start working on your homework. Got some good practice problems about sampling distributions and means for you. So good luck with that. Hope to see you all soon.